Hi guys, it's Mrs. Bird. As promised, here are the video notes that will correspond with the packet that I handed out in class today. So please have that in front of you. All right, let's start off by doing this warm-up activity that's on the first page where it talks about the jackrabbit and the number of hops and distance covered. If you could just look through this and do questions 1 through 6 on your own. I'm going to give you about 3 minutes to do that, and then we'll start talking about them after 3 minutes. But if you could, please, on your own, go ahead and try to answer questions 1 through 6. Take about a minute more to finish the first page. Okay, so we need to graph the number of hops the jackrabbit takes to the distance covered. All right, so we're relating number of hops to the distance covered. So first we'll graph 210. We're going to go to the right 2 and up 10 and put a point there. That's saying for every 2 hops, he's covering a distance of 10 feet. All right, at 4 hops, he's covering 20 feet. Put a point there. At 6 hops, 30 feet. Put a point there. 8 hops, 40 feet. We'll put a point here. And at 10 hops, he has covered 50 feet. All right, let's connect those. There we go. All right, so now that we've plotted those, question 2 says, does this graph go through the origin? Does this graph go through 0, 0? Sure it does. When we connected those points, our line would go through 0, 0. Why does this make sense for this scenario? Well, hopefully you said because if the bunny doesn't hop anywhere, then he won't go, he, there will be no distance covered. So why does this make sense for the scenario? Well, 0 hops, we'll say, equals 0 feet. 0 feet. Okay, and you can phrase that any way you like, but basically, if he doesn't go, hop anywhere, then of course there's no distance covered. All right, question number 3 says, how would the graph look different if the jackrabbit hopped a shorter distance each hop? Well, let's see. Here at 1 hop, he's covered 5 feet. At 2 hops, 10, so on and so forth. So let's say that at 1 hop, he has only covered 2.5 feet. So I'll put a point here, which means that if he's going at a constant rate at 2 hops, he would cover how many feet? 5? Sure. And at 3 hops, 4 hops, so on and so forth. What is the difference between the line that's given, that we graphed earlier, and a line that would go through these points? Well, it'd be less steep. Hopefully you're using some of the vocabulary that we've been going over this unit. This line is less steeper than the original line that we drew. So how would the graph be different? It'd be less steep. And again, you can phrase that any way you'd like. All right, what equation could be written to represent this data? Hopefully you're thinking about equations in slope-intercept form, as we've been um, covering quite extensively the last few days. So slope-intercept form is y equals mx plus b, where m is our slope, good, and b, the y-intercept. Okay, so if we're writing an equation to represent this data, let's start with y equals, our slope is what? Now I'm going to take this other line off that we drew, just so we don't get it confused with our real data. Okay, so hopefully you wrote the equation y equals 5x, 5 being the slope. In other words, we have to rise once and rise 5 units and run 1. We got to pay attention to our units. All right, so 5 over 1 is our slope, or just 5. And then plus 0. Why 0? 0 represents our y-intercept, and we just talked about that line crossing through the y-axis at 0. Just to clean that up, make it a prettier equation, y is equal to 5x. Okay, hopefully you got that. All right, what does the coefficient represent in this equation? Our coefficient being 5. What does that 5 represent? Well, that coefficient represents, number 1, our slope. We've already discussed that. But this also represents our unit rate. When we began this unit, we began with quite a bit of work on unit rate, which is just saying that for every 1 unit, what are you comparing it to? For example, here, for every 1 hop, how far has the bunny or the jackrabbit, how far has he hopped? Well, he's gone 5 feet. All right, so the slope tells us the unit rate. All right, and what do you notice about the ratio of distance to hops? Well, again, the ratio of distance to hops, that's rise over run, is equivalent to the slope. All right, the ratio of distance to hops, so distance to hops. Remember, a ratio can be written in 3 ways. We commonly write it in math as a fraction. So if we're looking at the ratio of distance to hops, that's 5 over 1, which you'll notice here is the same as the slope and unit rate. These are synonymous with each other. All right, let's keep going. Flip over to the next page. Now the next page is mainly notes. Again, in order to get your credit, you need to show me that you've gone onto this video, listened as I walk you through these these few problems. All right, so the first one, and we talked a lot about distance time graphs in today's class. You guys did a wonderful job of making up pretty elaborate stories about these distance time graphs. So we'll continue with that here. All right, so on the first part just says plotting distance against time can tell you a lot about motion. Let's look at the axes. We talked a little bit about this yesterday, or alluded to this. Time is always plotted on the x-axis. Remember my saying, time waits for no one? Because time can also be considered the independent variable. All right, time is not dependent on anything else. The further to the right the axis, the longer the time from the start. Distance is plotted on the y-axis. The higher up the graph, the further from the start. All right, and then distance would be considered our dependent variable. Okay. Remember, in some of these graphs, we won't be relating time to distance. So you have to remember that the independent variable goes on your x-axis and the dependent on your y-axis. When you're graphing time, time will always go on your x-axis because time is almost always your independent variable. Here's the next part. If an object is not moving, a horizontal line is shown on a distance time graph. You guys did a great job with this yesterday. Whenever we see a horizontal line, this is saying that we are at rest. Circle that. A horizontal line means we're at rest, which makes sense, right? Time is continuing, so we're still moving forward. The time is still moving forward, rather, but distance is at a standstill. It's not increasing. It's not increasing as time is increasing. Makes sense? All right, the next part says if an object is moving at a constant speed, it means it has the same increase in distance in a given time. All right, constant. Whenever we see a line or we have a linear equation, we're saying that something is traveling at a constant speed. Constant speed is shown by a straight line on a graph. All of these equations we've been graphing over the last 3 weeks have been linear equations. They've all made a straight line, which means they all represent a constant increase, or in this case, a constant speed. Something is increasing consistently. All right, and then the next one says, let's say we're looking at two moving objects. We talked a little bit about this in the warm-up we just did. Both of the lines in this graph show that each object moved the same distance, but the steeper dashed line got there before the other one. All right, here's the dashed line. It's steeper, that means that it's moving more quickly. Underline this. A steeper line indicates a larger distance moved in a given time. In other words, a higher speed. The steeper the line is, the quicker you're going. Again, both of these lines are straight, which means the speeds are constant. They're traveling at a constant speed. All right, and then that last graph at the bottom shows what acceleration looks like, which is not constant and is a little more realistic, especially if we're talking in terms of cars, right? We start off a bit slower than when we would when we really get going, say, on the highway. So the line on this graph is curving upward. This shows an increase in speed since the line is getting steeper. Starts off less steep and is getting steeper as time is increasing. In other words, in a given time, the distance the object moves is change or getting larger. It is accelerating. Circle that. All right, keep these things in mind as we continue on through this packet. All right, the next page, we are going to look at some distant time graphs, as we did in today's class, that represent the motion of a car. We're going to match the descriptions with the graphs, and we're going to be sure to explain our reasoning. All right, so let's start with, let's see, I'm actually going to split the screen so we can have our notes up on the left side and relate them to the right, just in case we need to. All right, so number one says the car is stopped. Which one of these represent the car being stopped? Hopefully you said C. All right, same thing we said in our notes here. When we have a horizontal line, this means that we are at rest. The car is at rest. Let's say it's at the gas station. Okay, so for C, we're going to put C matches description. Where are the, I'm sorry, 1 matches description C, or graph C. So I'm going to put a 1 here. Why? You put that in your own words. We just talked about it being at rest, so you want to make sure that you elaborate on how that line represents being at rest. All right, let's look at the second scenario. The car, oops, here we go. The car is traveling at a constant speed. Whenever something is constant, we're looking at a line. Very good. So we're looking at A or B. Which one is showing that the car is traveling at a constant speed? Okay, both are saying showing that it's traveling at a constant speed, but only A um, is showing that we're simply traveling. We're not going back to where we started from. All right. So scenario 2 goes with graph A. Graph A matches scenario 2. I would like you to fill in, based on what we just talked about, the reason why. Use good vocabulary like constant, um, linear, things like that. All right, so, and feel free to stop this video at any time if you need more time to write things down. But number 3 says the speed of the car is decreasing. Okay, so we've already considered A and C. Which one of these, B or D, shows that the speed of the car is decreasing? B or D? Which one? Hopefully you said D, right? Here's a steep line here, and then it's gradually tapering off, going closer to actually at being at rest, okay? So the car is quickly going fast, 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 and then kind of tapering off and getting slower and slower, almost to a standstill. So description 3, the speed of the car is decreasing, um, relates to graph D. So 3D. Let's put a 3 here. All right, and then the only one left is graph B. So let's see if that matches 4. Sure it does. The car is coming back. We talked a lot about this in class today. Again, you guys came up with great scenarios. Um, but to show that we're going back to our original location, the line would be going down. Okay, that doesn't mean you're going down a hill. It just means that you're going back to your starting point. The car is coming back. All right, so write all of that down. And that actually ends our video notes. You can stop here, but you're more than welcome to continue through the packet if you'd like to get ahead. But I only made you responsible for getting up to this page. So you're more than welcome to stop the video now at that page. However, if you would like to continue, please feel free to proceed with the rest of the packet and get a little ahead. Alrighty, so let's move on. Again, feel free to pause, rewind as you feel necessary. If you need more time to write or just think, feel free to pause. All right, let's see. Let me erase some work I did here earlier so we can do this together. Let's go to the next page. If you haven't stopped the video, thank you. We'll keep going. All right, I want you to start with this warm up here on the side. You may not have room on your paper, but just do it off on another sheet of paper or in the margins of the paper that you have. But I want you to start with this warm up. It says James bought a 12-pack of soda at the grocery store for $3.49. He plans to sell the sodas individually to raise money for the FBLA. First, we want to find out how much did James pay per soda. You know what? I was going to have you do it on your own, but let's do it together. Let's bring up a calculator here. You can do this by hand. Feel free to do that, but we're going to speed things along by calculating. All right, so how would we determine how much James paid per soda? He bought a 12-pack. What is the unit rate for the soda? In other words, how much did he pay for one soda? All right, we're going to take $3.49 and we'll divide that by 12. What does that give us? About 29 cents. We'll say about 29 cents. Question 2 asks, if James sells each individual soda for 75 cents, how much profit will he make in total? All right, remember he has 12 cans. So we're going to take this 29 cents and we're going to subtract it from 75 cents. He's selling them for 75 cents and he only paid 29 cents for each. So we're going to subtract. Let's start. Okay, so we're going to subtract, and you can probably do this in your head, but I want you to see the calculations. 75 cents minus 29 cents. Let's see. Might not put the decimals in there good, but. All right, did you get 46 cents? Okay, so he's making 46 cents off of each individual soda. But he has 12 sodas that he's selling. So we're going to multiply this by 12 and see what we come up with. How much? Okay, $5.52. For some reason my decimals didn't get in there, but that's all right. $5.52 is the profit that he would make off of a pack of soda. Not bad. All right, number 3, we're going to sketch the graph of the relationship between the number of sodas sold to the selling price. Go back and think independent and dependent variable. Doesn't the selling price depend on the number of sodas you have? Okay, so let's go ahead and label our graph. Number of sodas, we'll just increase this by 1 will be our units. And this is just a sketch. So on and so forth. All right, and then our selling price, we can go by 1. We can go by, let's say, 50 cents. If you want to go up by $1, that's fine. If you want to just go up by 75 cents, either way is fine. Let's go up by 50 cents. All right, 50 here, $1, $1.50, $2, $2.50, so on and so forth. This is just a sketch, so not exact, but after one soda, he has sold it for 75 cents, so we'll say about there. 2 sodas, $1.50. 3 sodas, how much is that? All right, so it increases constantly. But this would be the graph that represents the data that we have here. All right, keep these things in mind. The main thing I wanted you to take note of is unit rate, which is here, and how we're going to set up our graphs once we start graphing these things. All right, so let's move this out of the way. And go ahead and actually I won't move that out of the way. We'll just go ahead and work through this. All right, so at the top of the page that says interpreting from graphs, it says a relationship between two quantities is proportional if the ratio between the quantities is always the same unit. Proportional relationships can be represented by the equation, circle this, y equals kx, where k represents a constant. The graph of the proportional relationship would be a straight line through the origin. Again, when we first started the unit, we did talk about what would make a graph proportional, represent a proportional relationship. We talked about it having to go through the origin, 0, 0, and that it's increasing by a constant, or it makes a straight line, or the slope is the same. All of those things would represent a proportional relationship. So let's start off with this scenario. Ramon's Ramon raced Angel and Carlos in a 50-meter dash. Ramon's results are shown on the graph. What does the shape of the graph tell you about Ramon's speed during the race? Hopefully you would say to yourself, he's going at a constant rate. Explain how you use this graph to find the unit rate for Ramon's speed. Well, remember, we just talked about unit rate. We're looking for the 1 second mark. All right, so at 1 second, how far has Ramon traveled? He's traveled 5 meters. So you can use the graph to find unit rate by finding the slope. Right? He rise over run. His distance increased by 5 times 1. All right, let's look at Angel. We're not given a graph for Angel, but it tells us that Angel's data during the race can be described using the equation y equals 4.5x. And we're going to explain how we can find the unit rate for Angel's speed from just this equation. I'll rewrite it down here. Y equals 4.5x. Well, let's go back up to Ramon's. Let's see if we can write an equation for Ramon's graph. Now, in our notes here, it says an equation can be written as y equals kx. Does that look familiar? Hopefully you're saying that it looks like the equation of a line in slope-intercept form, which we've talked about is y equals mx plus b, where m represents your slope and b represents your y-intercept. Okay, so we wrote an equation for Ramon's line. It would look like y equals, his slope is 5 over 1, so 5x plus b. Why is there no plus anything here? Okay, hopefully you said it's because the line goes through 0, 0. The y-intercept is at 0, 0, which makes sense. If no time has elapsed, Ramon would not be going anywhere. All right, so y equals 5x plus 0, or we'll leave it like this, is 5x. Now that's Ramon's equation. Let's relate that to Angel's equation that was given to us down here. All right, where can we find Angel's unit rate just by looking at this equation? Good, hopefully you said 4.5 is her unit rate. Earlier in our notes, if you flip back, our unit rate is the same thing as our slope. All right, let's look at Carlos down here. For Carlos, we're only given a table. It says Carlos ran the race at a constant speed. The table shows distances Carlos traveled during different times in the race. All right, so at 2 seconds, he's traveled 9.5 meters, 4, 19 meters, so on and so forth. If we're writing an equation, actually it asks us to plot the data first, so let's do that. It says plot the data in the graph to show Carlos's speed during the race. What goes at the bottom? Time, good, in seconds. And across the y-axis, this would be distance. Excuse my messy handwriting. All right, let's go up. Let's increase at the same, using the same scale as, who's that? Ramon's up here. So it increased by 5 up there. Let's increase by the same here. 5 meters, 10, 15, 20, 25, 30, 35, 40. We can stop there since we only go up to 38. All right, so at 2 seconds, he's gone 9.5 meters. We'll put a point about there. At 4 seconds, about 19 meters. So we'll put a point there. At 6 seconds, he's traveled about 28 meters. We'll put a point there. At 8 seconds, he's traveled about 38 meters. So we'll put a point there. All right, so explain how you can find the graph, how you could use just this graph to find the unit rate for Carlos's speed. Well, how can we find the unit rate? By looking at the slope of the line. Right? What's our slope? How do we get our slope? Rise over run. You could look at just the table by simply dividing 2 into 9.5, which gives you 4.75. So for every 1 second, he's traveled 4.75 meters. All right. Or you could look at rise over run here. Here's 1 second. About how far up would we go to get the distance that Carlos has traveled in 1 second? All right, go over to 1 and look up on the graph. Let me go ahead and connect these points so we can see how his line would look. Okay, so a fair estimate here would be about 4. For every 1 second, he's going about 4.75 meters. To get the exact, you would divide 2 into 9.5 or 9.5. All right, write your description. I'll sum up all of that, what we just said here for number 2. Write a good description there, a good explanation. So who won the race? Well, we've written equations for Ramon and Angel, so let's go ahead and write an equation for Carlos since we know his unit rate or his slope. Write that off to the side. Y equals, what's his unit rate or slope? Good, 4.75. X plus 0. Remember, our line goes through 0, 0, but we don't need to put 0, 0 in our graph. So who won the race? Hopefully you said Ramon won because his unit rate is higher, his slope is higher, if we graphed all 3 of these, his line would be steeper than Angel's and Carlos's. So who won the race? Ramon. Higher unit rate. Steeper line. All of these are explanations of why Ramon would have won the race. Higher slope, etc. All right, okay with that? All right, flip over to the next page. Have it on another slide here. All right, suppose Ramon's twin brother Ricardo also runs in the race. Ramon gives Ricardo a 10-meter head start in the race, and they run at the same speed. So this graph shows the results. Ricardo is represented by the dotted line. Ramon is represented by the solid line. So first, let's write an equation to represent Ramon's position. We're looking at the blue line. All right, let's start with y equals. Our slope comes next. So we need our slope, but we don't have our y-axis labeled. So let's go back and label this. We were relating time in meters. I'm sorry, time in seconds, and distance in meters. So time in seconds and distance in meters. And meters. It told us that Ramon gives Ricardo a 10-meter head start. So that means Ricardo is starting at 10, which makes our scale here 5, 10, 15, 20 as before. All right, so again, if we're writing an equation that represents Ramon's position, y equals, let's find his slope, rise over run, 5 over 1, or 5. So 5x, do we need plus anything? No, his line goes through the origin, so plus 0 is appropriate. Or just y equals 5x. So what do the points 0, 0, and 0, 10 represent on the graph? This point here, and this point here. Sure, their starting point. Are the lines parallel? Yep, they're parallel. How do we know? Well, we could look at our slopes. If the slopes are the same, then we know we have parallel lines. That means they're traveling at the same speed. It's just that one started before the other. All right, so are the lines parallel? Yes. You write your own explanation there. Number 4x, Ricardo says that Ricardo runs at a constant rate of 5 meters per second. It has a head start of 10 meters. Write an equation of the line that represents Ricardo. Okay, so Ricardo is our dotted line. And I always start with y equals. What's our slope or our unit rate? We're rising 5, running 1. So same unit rate. Here we'll have a plus 10 y. Yep, we're looking at our y-intercept, or our starting point. Ricardo started, had a 10-meter head start, so we're going to put plus 10, indicating his head start. And we already talked about this, but go ahead and fill that in. What is the unit rate for Ramon? Unit rate is 5 seconds per meter. Same with Ricardo. So we'll say the unit rates are the same. All right, so listen, I'm going to end it here, but I would like for you, if you would like to get ahead a little bit, to do these problems 1 through, let's see, 1 through 4 on your own based on what we just did here. Work through those, show it to me when you come in the next day we have class, and we'll move you on from there. Enjoy. I enjoyed you. Thanks. Bye.